What protein folding is all about is that your DNA is, defined through genes, and these genes get read by proteins in your body and get transcribed into new proteins. And so you have this sort of idea of a sequence, right? Because it's always the same in the sense that the same genetic sequence will result in the same amino acid sequence. And proteins are just made up of amino acids, with caveats. There's always caveats in biology. As a general rule, that is true. And so the game is sort of figuring out, given an amino acid sequence, what is the 3D shape of this protein going to be? Because the function and the behavior of this protein is dramatically determined by its structure. The most important piece of information you could have about a protein if you wanted to understand how it's going to behave. And certainly if you want to drug this protein, or you want to design your own protein, then knowing its structure is critical.
Dive into the intriguing world of deep technology and its intersection with business on Technocracy. We're your hosts, Ajay and Loong. Let's explore the breakthroughs and people shaping the future of technology. Technocracy Podcast.
I have an interesting way to start this podcast. So I have a graph to show you, and you can tell me what you think it is. And
all right. Oh dear.
It's not crypto.
All right.
Okay, so this is the graph.
Is that the US? Is this something to do with the US?
No.
No. Anything to do with NVIDIA? No clue then.
Okay. This is cocoa prices. So the things we make, the thing we use to make chocolate, which is insane if you think about it. Like over here in 2022, it was like, $2,500 per ton of cocoa. Then it pumped all the way up to, I say pump like it's a stock, but yeah, it pumped all the way up to 12,000 at like April 2024, and now it's sort of settled at 9,000. But
so I remember hearing about that. I remember hearing about that because of the way that there was some natural disaster that hit the west coast of Africa where all the chocolate comes from. But I didn't realize the prices were still really high. Like that hadn't been resolved.
Yeah. So you're exactly right. That the reason is purely based on supply. So we had 104% increase of cocoa prices this year. And there was a 14.2% drop in global cocoa production for 2023 to 2024, which doesn't seem like a lot if you think about a 6x price increase for a 15% decrease in production. But yeah, the West Africa issue, I think there's actually a bigger issue with the supply chain, more than 14%. I think it's probably more than that because West Africa was hit. And I think West Africa is 70% of the world's cocoa, which I didn't know until...
Yeah, I didn't know that either.
Into this, yeah. So apparently all our chocolate prices are going to increase in the next few months. So
yeah, no kidding.
Yeah.
So this was, if you think back to our last podcast where we talked about, we did our moonshot game, and we talked about trying to predict what everyone wants to eat and then modulate supply and demand based on that. You can't get around these kind of natural events that are often black swan. You can't really, I don't think you can predict them. We're probably a long way from ever being able to predict these kinds of things. So even if you perfectly made food in the proportions that people wanted, things like this will happen and then just mess it all up anyway.
Yeah, I didn't realize how sensitive the supply chains were in terms of pricing. So even coffee, if you look at it, went up almost 2x this year, which is pretty wild. I was noticing
is that also due to the west coast of Africa? Is this the same cause, or is there something else going on?
I think it probably is a supply issue, but I don't know if it's to do with Africa. I looked at the cocoa thing and then I went to this graph here, clicked month to see what had the most change in the month. And so I was looking at some of the other commodities, but coffee was interesting.
This is the canon example of why future markets and derivative markets need to exist, right? So imagine that you're a cocoa farmer and you don't know what the price of cocoa is going to do, right? So for example, if you're producing cocoa right now, you can be pretty confident that the price is probably going to drop from here as the supply chain sort of sorts itself out. And the issue is you don't know what price it's going to drop to, or maybe another natural disaster is going to hit, the price is going to skyrocket. So how do you finance the endeavor? So you're going to attempt to deliver some tonnage of a commodity, and you don't know how that price, it's going to take you, let's say 6 to 12 months to produce that commodity, and you don't know how the price of that's going to change. But your prices, the cost of producing the commodity, are pretty much set today, right, as you begin. And so the idea is that by owning, let's say 10 tons of this commodity, you're naturally long that position, 10 tons. And so if there's a futures market, you can go into the futures market and go 10 tons short on that futures market. And then it doesn't matter what happens to the price. If it doubles, then yes, the value of your commodity has doubled, but the value of your short position has halved. And so they offset each other perfectly, and you neutral yourself out. And on the other side of that trade is people who are just betting on these kinds of events, or based on their knowledge of supply chains, politics, whatever it is that they're trying to predict the price going up or down. So it's part of the reason why these kinds of instruments, while they seem really bizarre at first glance, actually make a ton of sense. And where I guess they came from, in the world of crypto, it doesn't really make sense. Maybe from the perspective of miners, who you can kind of think about that as a long-term commitment to producing a commodity. But yeah, they're critical for stable supply chains.
In practice for futures, I'm guessing I don't actually know how some of these companies operate, but let's say a chocolate company, and they're trying to insulate some of their positions using futures. They're probably only buying a year out, 6 months out. Are they buying futures for 5 years? Probably not, right?
I don't know. I have no idea. I guess it depends on the commodity, right? If you're pulling oil out of the ground, you can bet that same company in the same country with the same political setup is going to be pulling oil out of the same place in the ground for the next 5 years pretty safely. So you probably have longer term options contracts available. Whereas commodities are very seasonal. They're going to change every year based on the weather. So maybe they're shorter term. Maybe they're only season by season. I mean, you could easily just go onto a commodities market and have a look at the different timelines for the different options.
Yeah, that makes sense. I think when I looked into this, I think the reason why chocolate prices hasn't increased as as the prices of cocoa increases, because they're still eating through their supplies, or they have futures to insulate some of it. Right now, we'll only really see the knock-on effects in 6 to 12 months if it continues, right? But if it corrects, and I'm looking at some of these other graphs, it looks like it just spikes and then comes back down if there's a one-off event. So it doesn't seem like they really last for...
And so sometimes what that spike is that when you don't know what's going to happen, then there's this over-demand where companies say, well, we're just going to buy up stock now so that we have it now, which causes a massive inflation on whatever the underlying good or service is. Because people don't, if there's some unpredictable amount of time before this thing resolves, then people try to insulate themselves from that as well. You don't want to be the only chocolate company that can't get access to cocoa, right?
Yeah. There should be a personal futures market where you can just buy your toothpaste for the next 2 years and just lock in the price today, and all kinds of other stuff. And if you do a group buy, it might work. Where
but the problem is who takes the other side of that? Who's betting that the cost of toothpaste is going to go down? No one, right?
Yeah, true. If the consumer wins, and someone has to take the loss. Okay. Well, yeah, that's the first thing I had for you. Very small one, but thought it'd be an interesting way to start the podcast, because everyone's looking at Bitcoin prices and seeing all these rises. And I was looking at other J-curve graphs, and the cocoa price was oh, interesting. I don't actually know. Can we make money off that? If we were to see this cocoa price thing, do you just buy the commodity?
I don't know. I mean, maybe. So you don't want to end up in this situation where, do you remember in the pandemic that the price of oil went negative?
Yeah, and there were people trying to get rid of it because they couldn't store it, right? The storage space.
So you had all these idiots buying futures on oil and not realizing that when a future matures, you have to take ownership of the commodity under the future. And so these people were like, oh, my future on a ton of oil, or 1,000 barrels or whatever, is going to mature. And I'm just some random bored trader. I don't have anywhere to put this. And so they had to start flogging them. And it drove the price negative. Because if you think about it, if you're in a situation where you cannot store 100 barrels of oil, you literally going to pay someone to take it off your hands. And so the price went negative. So yeah, you have to be careful. You could bet $10,000 on cocoa, but the last thing you want is that $10,000 worth of cocoa supply rocking up at your front door. And then it becomes worthless because you can't, chances are you're not storing that in a manner that's compliant with regulation, and therefore you can't unsell it as its fundamental thing, which is food. So you probably just screw yourself if you're not careful. I would think that there's some sort of framework around who's allowed to trade these futures for that reason. You don't want just a random guy at home suddenly having 1,000 barrels of oil. Surely you have to be some kind of regulated entity. So I don't know if individuals can trade on this kind of stuff.
So this is a more unhinged episode. I think all of the ideas we both brought to the table are pretty random. There's no rhyme or
there's no connectivity
to them. Yeah,
well,
but
I want that's proximal in terms of like it's relevant today.
Okay, go for it.
So I think it's every year, maybe every 2 years. I think it's every year. There's a thing called CASP, which stands for the Critical Assessment of Techniques for Protein Structure Prediction. I don't know why it's CASP because there's a lot more letters in there than CASP. But anyway, so this is this big conference where everyone gets together every year and they basically try and fight for who has the best protein structure predictor. And the winners were just announced, and they're holding the conference as we speak, which means that by the time this episodes get released, it will have happened. And so I just kind of wanted to like touch on protein folding because we talked about it, I think, earlier in the year, maybe in the previous season of the podcast. But the world of protein folding has dramatically changed since AlphaFold. So
AlphaFold 3 came out, right? Like a couple of months ago?
So a lot has happened since the OG formulation of AlphaFold. So we're already on AlphaFold 3. So the original AlphaFold wasn't too impressive. AlphaFold 2 really changed the game. It just beat all the benchmarks quite dramatically and was a fundamental change in approach to the way that we had been thinking about protein folding. And I think that was the most interesting part of it. So just to give our listeners a bit of a recap, what protein folding is all about is that your DNA defines your genes, and these genes get read by proteins in your body and get transcribed into new proteins. And so you have this sort of idea of a sequence, right? Because it's always the same in the sense that the same genetic sequence will result in the same amino acid sequence, and proteins are just made up of amino acids. With caveats, there's always caveats in biology, but as a general rule, that is true. And so the game is sort of figuring out, given an amino acid sequence, what is the 3D shape of this protein going to be? Because the function and the behavior of this protein is dramatically determined by its structure. This is sort of like the most important piece of information you could have about a protein if you wanted to understand how it's going to behave. And certainly if you want to drug this protein, or you want to design your own protein, then knowing its structure is critical. And so this has been a competition that's been going on since like 1994. CASP happens every 2 years. So it's been going on since 1994. We're up to CASP 16. And in 2020 was when AlphaFold 2 was released and when everything sort of like a big hoo-ha. Actually, maybe it was CASP 15. Anyway, since then, AlphaFold 3 has also come out. And AlphaFold 3 made an improvement on AlphaFold 2 in the sense that not only did it perform better in the benchmarks, but it was also able to make predictions for non-protein entities. So CASP has expanded to cover more than just proteins. And it can now cover nucleic acids, so like DNA itself as a shape, and RNA molecules, which is sort of the intermediate between DNA and an amino acid sequence. People might be familiar with RNA molecules from the RNA vaccines that were produced during the COVID pandemic, trying to predict the structure of these things as well. And because biology is complicated and messy, all these different molecules like to interact with each other. So proteins interact with each other, proteins interact with DNA, they interact with RNA, et cetera. And so there's this challenge around, predicting the structure of just one protein by itself in isolation, but then also a challenge of predicting protein complexes next to each other as they interact, and then protein DNA complexes, protein RNA complexes, and even protein small molecule complexes, which is such a special field that it has its own thing called docking and its own competitions, et cetera. And AlphaFold 3 for the first time kind of unified all these and said, can we just dump all this information into a deep learning AI and get it structure predicted out the other side? And turns out the answer is yes, and you can do this reasonably well. And so AlphaFold 3, unsurprisingly to anyone, wins the current CASP benchmark. The Yang group is still at the very top of the rankings, and they're the lab that produced AlphaFold. But this segment is actually maybe a little anti-rant on protein folding, because one of the things that has changed since last CASP is it's become standard now almost for the high-performing models to no longer be published. So they don't publish the code that was used for training them. They don't publish the parameters that they ultimately trained the model to have, or they don't publish the data that it was trained on, or some combination of all three, or they're licensed in a very, very restrictive way. So AlphaFold 3, for example, is only available on a server. So you cannot access it. You cannot access the architecture, the weights, anything. You just submit your sequence and it gives you back the predicted structure, and it can only be used for non-commercial purposes. So this sort of shows that, at least according to the free market, protein folding is now getting to the point that it's good enough that it's really making an impact on drug discovery efforts, because companies are starting to lock down on them and not actually publish them. And even research groups are starting to realize the potential value of the IP that they're generating and also locking that down. So one of the cool things that happened recently in the last month or two was the release of this new model called Boltz-1. Now, this is a thing that happens a lot in the AI field, which is that people will do some really cool proprietary shit, and then within a year, within 6 months, some absolutely awesome research lab will produce an open source version of it. And Boltz-1 is really exciting because it's the first variant of AlphaFold 3, and there are many variants that have been created. But it's the first one that's basically unrestricted in its licensing. So it's under the MIT license, which is very, very permissive. They've published the code for training it. They've published the exact architecture. They've published the weights, so you don't even have to train it yourself if you can't or you don't want to. And it performs at the level of AlphaFold 3. And so there have been a number of blogs that have compared its performance to AlphaFold 3, and it's more or less within a stone's throw. So that's the article announcing what you're showing here on the screen and looking at its performance compared to a model called Chai-1. So the reason they compare to Chai-1 is that Chai-1 was one of the first AlphaFold 3 variants that was published. It's one of the more established ones. It is also proprietary, though, so it's not actually released, so to speak. You can't access it. Certainly not for commercial purposes. And this is a really interesting, it's a really cool project. Again, it outperforms Chai in many places. It's on par with AlphaFold 3. None of this is surprising. All these models are essentially the same model, just retrained, slight variations, so they're all going to be within an error of each other. However, I think the game for protein folding is also changing fundamentally. So not only has it changed to not just cover single proteins in the last many years, but it's now also moving, people in the field are starting to discuss dynamics and saying that, folding is one thing. And there are tons of people who've, picked out examples where folding gets it wrong. And there's questions around whether there's actually enough data that we'll ever be able to, that we're actually going to be able to predict this reliably. But people have also started commenting that the lack of dynamics is a huge issue. So before I comment on the dynamics, though, the state of protein folding right now is that you can get reasonably accurate predictions on what you might call natural proteins. But once you start making edits to them, they start getting the structure wrong. And this is critical that the field figures this out, because single mutations in an amino acid sequence can be the difference between having cancer or not. There are tons of examples of cancers that are caused by a single mutation in a protein that results in a change in function or a change in structure of that protein, and that ultimately leads to cancer. Or it can be, that's a mutation that maybe doesn't cause cancer, but it's one that you can take advantage of that can cure cancer. But for the most part, none of these models are able to capture that, what we call single allele mutations. So that's still an outstanding challenge. But the other outstanding challenge that I alluded to is dynamics. So when you predict a structure, you're getting one snapshot of a structure. But this is like me asking, what's the structure of AJ, right? And I could give an accurate 3D description of AJ, but it would only be one of the possible 3D descriptions, right? Like right now, you're sitting at a desk with your hand against your mouth, right? But there are times when you're standing, there are times when you're running, there's times when you're lying down. And these are all critical to a holistic understanding of how AJ works and how he functions. And if I wanted to attack AJ and kill him, it would be really nice to have a full understanding of how you move and your structure. And I'd be like, when he's sleeping, lying down, that's when he's most vulnerable. Let's get him then, right? But you don't actually spend most of your time lying down. And so if I just had a model that trained to predict your most average 3D structure, it probably wouldn't show me your weakest points. And for drug discovery, that's critical. So I think the game of protein structure prediction is maturing insanely fast, especially compared to the first decades. Still has a way to go with the single allele mutations, but still has a long way to go with thinking about dynamics and trying to give you multiple hypotheses for what a protein might look like, which, as you can imagine, is exponentially more complicated than a single structure.
How much variation is there in protein structures? I guess your point is that proteins
Massive.
Change and move in they're more like a blob. They don't really stay in a static sort of position, right?
I would say there's a high variance from protein to protein. So some proteins change massively over time, right? Even not accounting for any mutation. That's just part of the way they're just how they've evolved. That's their behavior. That's their structure is to be very dynamic. Some proteins are by themselves not very dynamic, but when they pair up with other proteins, the meta structure becomes very dynamic. Some proteins are globular and they don't really change at all. And they're just they're structural columns so that your cells can have a shape, right? And they don't really move at all. But a single mutation might dramatically change that structure. So it's complex because the answer is basically it differs from protein to protein, and the variance across the proteins is huge.
And then you mentioned that it's mainly trained on natural proteins. Does that mean proteins that naturally occur in the wild as opposed to proteins that you would create a random genetic sequence and sort of see what happens?
Exactly. So if you just were to create a random genetic sequence, you'd most likely get an unstable protein that just didn't even form, right? It just sort of like was a melted puddle. So all proteins are made of amino acid sequences, but not all amino acid sequences result in a meaningful, functional, sensible protein. And that's kind of what you're exploiting with these AI models, is that you're kind of relying on the fact that there's only a subset of these amino acid sequences that are possible. So there's 20 amino acid sequences, and proteins can be thousands of amino acids long, right? So think about it, you've got 20 to the power of 1,000 possible combinations. There's no way you could accurately predict that entire space. You're relying on the fact that the vast majority of those sequences are not real in the sense that they're actually result in something interesting.
Okay.
But the databases that we have, that we train on, they're like hundreds of thousands of structures big. And so like you compare that, right? Hundreds of thousands of structures, millions maybe if you include all the proteins, not just human proteins, et cetera. There's still nothing compared to 20 to the power of 1,000.
When you say things have like really accelerated in the last 6 months, like what is the difference? Just like the capabilities have improved beyond just amino acid sequence to protein structure, because now there's all these other things in there, or is like there's something else driving this? Like, would you call it an inflection point, like that we've hit?
Certainly, yeah. Okay. I would say AlphaFold 2 was definitely the biggest inflection point. Okay. I think there's probably been big inflection points behind the scenes, but again, because people don't publish these models, it's hard to tell. I think that when AlphaFold 3 was published and said we can do more than just structures, we can do structure complexes, and we can do like non-protein structures and complexes too, that dramatically changes the possible field of applications. So if you were a protein engineer, if you were interested in protein transcriptomes, right? There was a limited interest in AlphaFold because it couldn't really deal with the DNA side. Now there is a huge interest because you can model both simultaneously, and you can model DNA as well as proteins, and you can model them in complex. And so that applies to a broad range of things, right? So if you could only predict proteins, then people who are interested in proteins are kind of interested in your field. But if you can predict proteins and DNA and RNA and small molecules, and you can predict them all in complex, then that's basically all biologists and chemists are suddenly interested in what you're doing. And so the drive and interest drives innovation and research supply. Within the year, we got an open source variant of AlphaFold 3 that performs to the same level. And I think that the release of that open source will allow people to iterate much faster. And so I think Boltz 1 has a chance of being that inflection point.
Nice. I like it. I'm curious to see what you guys do with it as well. Like, are you doing any work with Boltz 1? I'm guessing.
We'll integrate it into our tech stack for sure.
Okay.
We won't innovate on top of it, but we'll make it available for people to use so that they don't have to be technical to use it. And we'll integrate it with all our other tools so that if you want to drug a protein and you don't know the structure, you can just say, I don't know the structure, but I want to drug it. And we'll say, okay, that's no worries. We'll use Boltz behind the scenes. Predict it for you.
I'm trying to think of a segue between protein folding and weather balloons, but I don't have a good one. So I'm
just go straight for it then. Yeah.
I'm going to tell you about weather balloons. How much do you know about weather balloons?
Nothing.
Okay. So we launch about 80,000 balloons a year just in the US alone. So there's probably hundreds of thousands of balloons across the world like that are being used for this. And they're all single use, right? So you just launch this massive balloon and put this thing called a radiosonde in there that just has a bunch of different sensors. It does things like altitude, pressure, temperature, relative humidity, wind speed and direction, cosmic ray readings, and geographic position. So you have all these thousands of balloons flying around. They're launched almost daily in some cases, every few hours in other cases. It really depends on the...
Why are they single use?
They're single use because they fly up in the air and they're just like, it's really hard to track them, right? It's just cheaper to launch these like single use balloons than to use aircrafts and things like that to like maybe do things. There are other technologies. So I was looking into this as potentially a business for me to start in the weather space, because I was like, okay, this seems really outdated. Why are we sending balloons that die within 2 hours and then we relaunch balloons over and over again? There is LIDAR technology that we can use to like basically looks like a massive cannon and you just like beam lasers into the sky and sort of determine what the weather is. The only issue is like you can't do it in the middle of the ocean unless you like have a ship with these LIDAR things in there. And B, still like the cost and the economics behind it still doesn't make any sense because weather balloons are just really cheap to make and deploy. There are other technologies used. So there's something called a drop sonde, which is like it's a radio sonde, but it's in an aircraft, and they do it when they have like a tropical cyclone or something. And so the aircraft will just sort of fly past the tropical cyclone.
What's a radio sonde?
Radio sonde is the detector used in the weather balloon. So it's a disposable, once-off, battery-powered instrument that just sort of like detects some of these different altitudes and wind speeds and stuff. A drop sonde is the same thing, except it's dropped from an aircraft instead of using a weather balloon. There is one company that's doing something interesting. So Windborne Systems, they have created balloons that last up to 40 days instead of 2 hours. So obviously a lot better. And they're working on an AI model called Weather Mesh, which allows them to sort of determine what sort of things are happening based on all these different sensors. 40 days of data, obviously a little bit easier to use than 2 hours worth of data. And also you can get into these areas which they call data deserts, which obviously if you only have 2 hours of flight time and you're launching from land, you can only get so far. But with 40 days, you can cover like in the middle of the ocean and various locations that you may not be able to detect otherwise. So yeah, I got into this rabbit hole because I was looking at the weather app on my phone, trying to determine when and if I should cancel my birthday party because of rain. And I was like, how are they even determining the rain like 1 week in advance and like 2 weeks in advance? So I sort of looked into it, and the weather balloon sort of thing came up, which was really interesting. The opportunity also is that weather balloons actually cause a lot of ocean pollution. So 70% of weather balloons end up in the ocean. And I think there's a researcher in Australia on the Great Barrier Reef. He collected 2,500 pieces of weather balloons across the Great Barrier Reef, which, I'm still using disposable balloons for this. Sorry?
200,000.
Sorry, 2,500.
Oh, okay. I misheard that.
Yeah. 200,000 I think would be a more pressing issue. But yeah, weather balloons. I think that there's something there opportunity-wise. Windborne is sort of, I feel like they've done something cool, but it's almost like a Band-Aid on an existing solution versus like what is the next evolution beyond
well, it feels like,
weather
like
balloons.
you can make the analogy to space travel, right? And like single-use rockets and convert them to like multi-use, where they can actually be somewhat guided. Because I would imagine that it's kind of annoying to also not have control about where your weather balloon goes, right? It's just like you release it and it goes where it's going to go, and you're like, well, that's actually not where I wanted to know.
I think Windborne has slightly more control over their balloons. I remember reading, like in one of their blog posts, that they had some sort of minor control systems where they could go up, down, and sort of push it.
We're just going to replace this with drones? Is this a drone thing? Where we just realize?
I think drones could be interesting. I think LIDAR is also very promising. It just depends like how you're going to use it. There's also the issue of like beaming lasers into the sky that like you got to go around like
randomly
aircraft traffic and all that kind of stuff, so it could be dangerous. But I think LIDAR is probably the most promising way for us to sort of do.
Yeah, see, I was going to suggest that you release LIDAR satellites, but that would be even more dangerous, beaming lasers into the ground.
Yeah, you'd rather beam it up than down, I think. So, yeah. Let me find the LIDAR weather thing. Where is it? Yeah, so it looks like this. If you're listening, it looks kind of like a tank. So this is the wind cube.
Well, they look really strange. It looks like a super miniaturized AT-AT.
Yeah. So anyway,
like a cartoon robot.
You're basically just measuring like the differences in energy being reflected back, and any disturbances to the waves that you're sending. So I think this works fine. You just got to figure out the economics around it, because the Meteorology Bureau is not going to use this if it's way too expensive. Balloons are just really easy to use at this point. You just fill them up with this like little gas canister and they just go flying off. So yeah, weather balloons.
Interesting. Are they still using supercomputers to model like actual weather predictions from the data that they're collecting, or have they actually moved to these like I know that DeepMind I think published a weather AI that just like outperformed the supercomputers, and you can run it on a laptop. Do you know whether they're
so
still
I think
using supercomputers?
DeepMind and Windborne are probably the two leading parties for AIs around weather at the moment. So I don't know like if it's increasing accuracy or how those models are actually doing, but yes, I think we're moving away from supercomputers at this point.
Pity. That means less funding for supercomputers. All
what's
right.
what's your next thing?
I'm going to segue from. I know how to do this segue. Okay. So, someone who has lived in Southeast Asia, you would have noticed something really funny about weather reports there, or maybe you didn't. I did when I first moved there, which is that in Australia, you just get the weather. In Singapore, you get the weather and the number of dengue cases in the last 24 hours. And this is because dengue is quite prevalent in Southeast Asia, and it's incredibly painful. If you've ever had dengue, you're a goner for the next 2 weeks. Obviously, if you're elderly, it can be very, actually dangerous. If you're immune compromised, it can be very dangerous. Most people survive, but people do die from it. But unlike in Australia, there's a big effort in Southeast Asia and South America as well to try and combat dengue. I think, it's a very common stat, but maybe not everyone knows it, that mosquitoes kill more humans than anything else. It's estimated that mosquitoes have killed more humans than literally any other thing, including other humans. So they are the biggest killer of humanity. And so trying to resolve the spread of disease by mosquitoes is a sort of an open problem that has garnered the interest of people for thousands of years. And what I wanted to talk about today was two of the ways that people are combating this. And one is in production and one isn't, so I'll caveat that first. So first we'll talk about the one that is in production. And it's by this company called Verily, which is actually a spin-out of the Google X Lab. So this moonshot game that we play, one of their ideas was this program called Debug, which is very clever. But basically what they do is they discovered that there's a certain type of bacteria that when it's called the Wolbachia, and when Wolbachia infects male mosquitoes, it basically makes them unable to have offspring with female mosquitoes that are not infected with Wolbachia. And so what they do is they have this crazy lab set up, and they actually, let me share the link with you so you can kind of scroll through it.
Didn't we already learn our lesson when we tried DDT and try to eradicate mosquitoes, and they were like, yeah, nah, we're gonna stick around anyway?
Absolutely. I will we'll get on that. We'll touch on that. But basically, so the idea is you have this crazy lab set up which feeds mosquitoes into this machine, and the machine are these single lanes, and the mosquitoes walk down this lane, and you have an AI that looks at it and determines whether it's a male or female, because the males can only not breed if the females are not infected, and males cannot spread diseases because they don't bite. So it's only the female mosquitoes that spread diseases.
They're determining whether it's male or female based on how they walk?
Yeah, the shape, size, and how they walk. Yeah.
Oh.
And then what they do is they infect it with Wolbachia, and then they put it into a batch, and then they release the batch into an area. And so these mosquitoes compete as mates, and then eventually are unable, the mosquito population is radically suppressed. And so in California, when they ran trials across 3 communities in over 6 months, they saw a 95% reduction in female mosquitoes in the control sites. And in fact, the more interesting part of that is that the error rate on that is within the bounds of people just moving between these control areas, right? Obviously, mosquitoes can fly between control areas. It's very hard to just set that up. So you set up sites and you conduct checks, but 95% is over the level where the remaining mosquitoes that you're detecting in that area may have just migrated from a nearby area. It may have nothing to do with your thing not being useful or working. So they found that residents living in those areas over the course of a year were 77% less likely to get infected with dengue. And so what they're doing now is they're actually starting to roll this out in places in Southeast Asia, in places in Singapore, in places in South America. So this is actually something that's done today already in the wild, because dengue is enough of an issue, and this seems to be enough of a sort of natural solution. Wolbachia is a real bacteria that exists in the wild that naturally infects mosquitoes. So you're kind of leveraging something that's already there, and I think that makes people a bit more comfortable. It's also the case that you're not fundamentally changing the mosquito's biology. And that leads me to my second point of conversation, which is slightly is equally interesting to me, is the idea of genetically engineered mosquitoes. And so there's this thing called gene drive, and basically what you do is you take CRISPR, which is this cool gene editing tool that we have, and you fundamentally edit the germline DNA of a mosquito to make them unable to breed, right? So you make them completely infertile. And this, you can actually sit it in the germline so that if what happens is you put it in the males, you release the males, they breed with the female, they produce infertile offspring. The problem with that is you're fundamentally changing the genetics of a mosquito, which might have unintended consequences. And so this hasn't actually been used outside the labs. I think there's been sort of like regulatory challenges with trying to get this done in the real world. And so to counteract this, what people are beginning to do is to develop anti-drive mutations. And so they're developing the opposite, where you can actually go in and you can genetically modify a mosquito to be resistant to this genetic modification. Or the effect of this modification. And the reason why that's a nice thing to do is that if you try to apply this to a control area, which is the next natural step for a study, and those mosquitoes leave the control area and this gets out into the wild, you can try to counteract that by then counter-releasing new mosquitoes that have new mutations that sort of like make the original mutation inert. Now, it turns out that that's wildly effective. So they use this thing called an aqua protein, which essentially makes the CRISPR protein stop working. I won't dive too much into how. But I just thought it was kind of crazy that if you just pause for a second and take a 30,000 foot step back, you say you're struggling to convince people that genetically modified mosquitoes are a good idea. And the way that you're going to solve this is by further genetically modifying mosquitoes to counteract the original genetic modification, which I think just kind of is a little bit of an insane idea. It's fighting fire with fire.
That's so interesting because we moved away from with the whole DDT thing. We tried eradicating them, it didn't work because they became resistant. So we started moving towards sort of like preventing them from reproducing by getting rid of water, like stagnant water, using mosquito nets, and like we sort of moved our strategy away from like trying to kill the mosquitoes to just like let's ensure the environment is right so that they're not reproducing as much or getting to us in the same ways. And now I guess we're moving back towards, okay, how do we suppress the populations in some way, right?
Because what you want like really rapid suppression. And that's the benefit of introducing infertility, is that it's very hard to mutate away from infertility because how do you breed, right?
Yeah.
Like it's almost by definition impossible to mutate away from that.
That's a good counter. That totally makes more sense than, because if they can't breed, then yes, they can't even build a mutation, which gives them resistance in the first place. So that's
and I think that's why you go after fertility instead of going after like a variant of Wolbachia that kills them, because then over time you would expect that you could you would expect the mosquito population to build resistance to that.
I just googled it. 700,000 deaths worldwide every year from mosquitoes. That's wild. 600,000 from malaria, 40,000 from dengue, 30,000 from yellow fever, and then Zika. There's no number for that, but Zika is also another vector-borne disease.
So, I mean, this is why there's such a huge amount of interest in dealing with mosquitoes, is because they're one of the largest. Well, they are the largest killer.
The fuck! I should have been way more paranoid about mosquito bites in Bali. I had like 5 or 6, and I was like, oh, she'll be right. Like,
yeah. So, I mean, interestingly, there's a single species, which is Aedes aegypti, which is responsible for dengue, Zika, yellow fever, and one other one that I'm not going to even try and pronounce. No. But anyway, the top killers are all from this one species. So
interesting. I wonder if anyone's trying to weaponize mosquitoes. Military's probably working on something.
Jesus. Yeah, biowarfare. There you go. That's my weather into mosquito segue. How are you going to fold it back?
Yeah, I guess if you want to store data and all the trials you're running, you need a better storage system, right? So.
Oh, we're talking about storage today. All right. I was wondering when this was going to happen.
Well, we're not even talking about that. So there's another storage tech that came out that like it's been around for a while, but there's some news that came out like 2 or 3 days ago in terms of efficiency bonuses for it. Have you looked into diamond storage?
I've heard about it, but I've not looked into it.
Okay, so diamond storage is interesting. I'm going to see if there's any images I can show. There is nothing cool. It's just like diamonds with lasers pointing out of it, which isn't necessarily visually helpful for this demonstration. But essentially what they do is they create spaces within the diamond structure. So diamonds are carbon. You remove some of the carbon by knocking them out with lasers, and you introduce nitrogen in there. And it creates something called a nitrogen vacancy center. And what you can do is essentially that nitrogen will hold like a quantum spin. and that spin can be, let's say, 0 or +1, plus or -1. And you can basically say that, okay, if it's a 0, we'll call it a 0, and if it's plus or -1, we'll call it a 1. It's not exactly how the programming works, but for simplicity's sake, like the spin is basically controlled using lasers, and that spin can be encoding a bit into
interpreter's data.
Yeah. And that's how the read-write sort of happens. The read happens because the spin state sort of has like a fluorescence pattern, and so you can sort of see what's happening there and sort of read it. The accuracy is not bad, but it's not perfect. It's about 99%. So there's 1% error rate when you're sort of reading back what you've written to it. It takes about 200 femtoseconds to write to it. What I didn't really understand is I don't know if that translates to like read-write speeds in terms of same thing with like megabytes per second. It is 200 femtoseconds to write 1 bit into the diamond. But I don't know what the reset time is, if you can just go from one
right. So, I mean,
another bit.
these kinds of like throughput metrics, you have to look at 2 values, right? The latency and the throughput. It's no good to say, oh, you can do, 10 gigabytes a second, but it's like you wait for 1 second, or like you wait for 10 seconds and then you get 100 gigabytes, as opposed to, a gradual reading and writing.
The density that we've hit is 1.8 terabytes per cubic centimeter. To put it in perspective, it's about 2,000 times more dense than Blu-ray.
Right. So
however, it's very similar to a hard drive.
Did you say 200 femtoseconds?
200 femtoseconds, yeah. So it's about 500 gigabytes per second read-write speed if you were to like immediately reset it, which I don't think is the case. 500 gigabytes per second is an insane read-write speed if you compare it to like anything else we have on the market. Its density also isn't that amazing. I think it's okay, but compared to like a hard drive, it's about the same, maybe twice as much. So I don't know if that really changes the game. Sorry?
What kind of hard drive?
Just like a standard hard drive is about 1 terabyte per centimeter squared, because we usually read-write to like a 2D surface rather than 3D surface. It's kind of hard to give an exact comparison, though one could argue that the third dimension adds like a lot more to the entire thing. If you were to create like a diamond hard drive as the same size and dimensions of a hard drive, then yes, possibly you can get much more sort of density. However, we've discussed tape drives, right? Offline, not on this. Tape drives are still slightly more dense because they wind up in a tape as opposed to like a spinning disk. So is diamond storage the next big thing? Not sure. I think it really depends on the throughput, like you said. And it also depends on...
the latency, not the throughput.
Yeah, it also... Yeah, you're right. Sorry. It also depends like what the cost per gigabyte is, because that's the ultimate metric that everyone's...
I was going to be my next question, right? Like a diamond hard drive sounds like it's pretty fucking expensive.
Yeah, I'm not sure if you need a solid diamond or if you can use diamond like, like dust, essentially.
And how resilient is it to its environment? Like you're encoding quantum spin state into this thing. Like, is it resilient? How long does it last? How does the data degrade over time?
Yeah, I think the biggest benefit that they're sort of pushing for is the fact that it's like very, very robust and resilient. So it should last theoretically millions of years, as opposed to a tape drive, which has 30 to 50 years, and a hard drive, which has 7 years. So,
and is there a read-write limit on it? So the other thing about like SSDs, for example, is that the more you read and write to them, the more the error rate increases. So they're only good for a certain number of reads and writes before the error rate becomes so high that they're practically unusable. Is that the case with these things? Like, how often can you use them?
Yeah, I don't think they touch upon the reusability of these, but it is interesting that a million years from now, potentially the data storage devices that sort of persist are like data crystals, like in sci-fi games where you're just like shoving a data crystal into a computer and sort of getting the data off it. So yeah, I think it's really interesting as a technology. I can see the purpose of it being like archival based and sort of like having that longevity beyond 30 to 50 years. But
so interestingly enough, to bring it back to life sciences, as always, one of the reasons why the original discoverers of DNA were where that original idea came from was this physics-centric understanding that one of the best ways to encode data would be in some sort of repetitive crystal structure that had some kind of variation in its pattern, but was, other than that variation, was fairly predictable, and that variation itself was predictable, and that led to sort of the hypothesization of like these DNA crystals. And obviously that's not actually how it ended up looking, but that was the original inspiration for going in that direction, that somehow the information about what it is to be human versus a mosquito is somehow encoded informationally, and it's most likely some sort of crystalline structure. And to some degree, you can imagine a DNA helix as it's a fairly repetitive, loosely speaking, crystal-like structure. We do call protein and molecule structure prediction, we do refer to it as crystal structures. So there's an element of like direct description of something as a crystal. So I don't know, maybe we should do the protein prediction after this. We could have done a perfect segue through all sequences of our discussion.
Sure. Yeah. Yeah. So what did we covered weather balloons, we covered protein folding, diamond storage, cocoa prices, and mosquitoes. I think it's a pretty broad spread.
Yeah, man. No matter what you're interested in, there's something in this episode for you.
All right. So what I've noticed, if you're still listening, we have about 20 times more views anytime we mention Elon Musk or SpaceX or Tesla or anything like that. So I'm just saying, I'm going to say Elon Musk and Tesla and SpaceX, and hopefully this gets 20 times more views.
You know what to do, right? You title the episode, "Can we do a SpaceX with weather?"
Yeah.
Can we Elon Musk the weather?
Clickbait.
Reusable balloons.
So if we did do that, and you've got to the end of the episode and you realize we have not mentioned that at all, then I apologize, but the game's the game, and you got caught. So.
You fell for it. Learn not to get clickbaited.
But if you haven't subscribed, would appreciate a subscribe. We're at 55 on YouTube. Would love to get to 100 before the end of the year. Great Christmas gift for both of us. And yeah, thanks so much for the support, and we'll see you next episode.